called factoring completely, is to factor or break down a polynomial into quote unquote the smallest or simplest factors possible. Okay. We're going to be using a new strategy for this, but maybe not necessarily new, but it's a strategy we can use. It's called factor by grouping. And believe it or not, we've already been doing factoring by grouping. You may not even know it. When we factor by grouping, we're going to group our variable or group our polynomial into smaller parts, and we're going to factor out the greatest common factor from two smaller parts, from the components, I guess you could say, of our polynomial. We're going to factor out the GCF from smaller groups within the polynomial. That sounds kind of confusing. At least I think it does. But maybe you don't. We've actually been doing this already. But you may not have realized it. It all starts, it's all predicated on factoring greatest common factors. So pulling out things that are in common amongst all the terms. So let's start with kind of some, I guess, relatively easy GCF ones. Is there anything in common amongst all these terms?
Y.
Y. So let's factor out a y first.
Y.
You get y squared minus 4y minus 12. To factor this completely, I want to break this down to the smallest possible parts to be multiplied together. So I've broken it down once by factoring out what's in common. But now I need to factor this. This looks like something I could break down further. Okay, so you could factor this either with a box and diamond like we practiced last chapter. You could factor pattern this. You could guess and check this. This actually breaks down to, what did you say, Nate? 62? This is the same as y minus 6 times y plus 2, and there's a y in front. So factoring this completely, none of those smaller factors can be broken down farther. It's as good as it gets. Let's do this middle one kind of quickly. 3 is in common, so we have 3 and an x, and it's left with what? X squared plus 10x plus 25. 3x is in common. X squared plus 10x plus 25. If it doesn't already, this needs to be jumping out at you as a special factoring pattern. Perfect square, perfect square. Middle term is the product of the square roots, double. This is a perfect square trinomial. This is x plus 5 squared. Okay. If it doesn't jump out at you, you could use the box and diamond, and you could play guess and check and get x plus 5 times x plus 5 and rewrite it as x plus 5 squared. Something times itself. Similar game. What's in common? 5. And how many g's is the most in common? 3 of them. And when I divide out 5g to the thirds, I'm left with g squared and 16. If this isn't already jumping out at you as a special factoring pattern, it should. how does this factor without using a box and dime, without guess and checking? How does this supposed to factor? Alex?
How come you don't change the sign?
It has to do with to show that you can multiply any two numbers subtracted times this quantity, and when you multiply them out like with a chart, you'd get the only thing left over would be a to the third minus b to the third. If you FOIL, you get a to the third plus a squared b plus ab squared. You get minus ba squared minus a squared b minus b to the third power. So you come back to this. Right. It's a pattern. If you want to use it, fine. If you don't have to.
Does using it?
Oh, I ignored Brandon in there. Anyways, let's use this. Use this idea to factor some cubics a little bit efficiently. 27x to the third plus 125. There's only two pieces, so I'd really love to hope that these are like perfect cubes. Is there anything in common between 27x to the third and 125? Any number that goes in both 27 and 125?
4.6.
Yeah, no, there isn't. There aren't any whole numbers. So then next ask yourself, well, this is x to the third power. So is there something times itself that is 27? Yeah, 3. So this is the same as 3x to the third power. What times itself is 125? It's the same as 3x to the third and 5 to the third. So then, if I know that this is the relationship, this is like my A, this is like my B. So, and they're perfect cubes that are added together. So you could use this sum of cubes formula to get an efficient factoring. So I know that this polynomial should factor to 3x plus 5, and then a squared, or 3x squared, plus 3x times 5, minus 5, minus 5, plus 5 squared. And we'll simplify this just to clean things up. So you have 3x plus 5. 3x squared is 9x squared. 3x times 5 is 15 x's. And 5 squared is 25. We'd be using the special factoring pattern to factor this down. 3x plus 5. 9x squared minus 15x plus 25. Similar game, but the second one, only thing, in the second one there's something in common you can factor out. Namely, -2 can go into both of those. If you factor out -2, and notice I'm going to factor out the negative because I'd really like the leading term to be positive. And also you can factor something else out. A d, and the minimum of the exponents is squared, so we'll go d squared. And what's left over is a d to the third, and a, conveniently, 125. Popular perfect cube. Oh, and I made an error. So I divide out -2 from each of these, that makes d to the third positive, and 125 divided by -2 is -125. Perfect cube, subtracted. So I get -2d squared. Difference of two cubes, a minus b. d minus 5. Perfect cube of 125 is 5th. And then a squared plus ab plus b squared, or d plus 5d plus 5 squared is 25. So let's see. If I want to factor a quartic, no, it's not a quartic. That's a cubic with 4 terms. A 4-term polynomial. If I want to factor a 4-term polynomial, I can't just use like the normal box and diamond that we've seen in the past. I need to factor by grouping. Is the main strategy. One way to factor by grouping is, maybe you've seen this in the past, is you like put parentheses around 2 of the terms, factor out what's in common, and then factor a second time. Has anyone ever seen that before? Oh, fire up then. We won't even bother you with that then. If I want to factor a 4-term polynomial, what I'm going to try to do is this. First, I'm going to try to find anything in common amongst all the terms. Is there anything in common amongst all the terms? 1. Any variables amongst every term? No. We can find things in common amongst any 2 of the terms, but not all of them. So since there's nothing in common amongst all of them, I can't factor something out to begin with. What I can do is this. Let's factor by grouping now. Let's try a box. And I already claimed to you that making a box is using factoring by grouping already. So what we're going to do is just going to put each of these 4 terms into our box. And make sure we put the first term first and the last term last. And we'll fit these guys, how about just in, doesn't really matter, but I like this one. I like this one. And you might be saying, what is this guy doing? You didn't even draw a diamond. How am I going to do this? That doesn't seem to really work all that well.
-27t squared.
What?
Is it squared or cubed?
It's supposed to be cubed. That's a total error on my part. It was just to make you stay on your toes, if you believe that. Okay. I told you before that when we use the box, what we're really doing is finding what's in common in each row and column. Well, let's follow that rule. What's in common in, say, this first column? If they're different signs, we'll go with the positive number. So we have a 3 and 1t. What's in common in this column? 5. Oh, now here's a good one. What's in common in this column? In this row? A 9 and we can get up to t squares. Is there anything? What's in common here? 1, and they're both negative, so we'll go -1. This is just the answer to a multiply problem. So here's a solution to a multiply problem that would give you these answers. So this polynomial could start by factoring to, say, 3t plus 5 and 9t squared minus 1. That would be one factor. Well, that would be one way to factor this. But I claim we can do more. I claim you can factor this even more. What? So of the 2 groups, of those 2 factors, which one do you have a chance to factor? The first one or the second one? The second one's only have a chance to. Is this a special pattern that we've seen? Tis is. Squared. Is this a perfect square? What's the square root of 9t squared? 3t. What's the square root of 1? 1. So it's saying that this thing is equal to 3t plus 1, 3t minus 1. Or this polynomial factor completely is 3t plus 5 times 3t plus 1 times 3t minus 1. Let's try this again. Let's try to factor this by grouping. So we'll start with, we'll use our grouping diagram to help us out. X to the third minus 63. And then we'll put these in whatever order you like. I like squared and...
Why don't you just like put them in the box?
Find what's in common. x 7 x squared -9. So this factors to x plus 7 x squared minus 9. And x squared minus 9 is a difference of two perfect squares. This is x minus 3, x plus 3. All right. How do we do this one? 10x to the, ooh, now we have fourth power. Holy cow, what's going to happen here? 10x to the fourth minus 10. First of all, is there anything in common? 10. So let's start by factoring that out. Oh no, there's only two terms. What could we try? What are some patterns that might help us? Yeah, we don't have a 4-through pattern. Look at that. What's the square root of x to the fourth? What times itself is x to the fourth? X squared. What times itself is 1? 1. So this is actually, if you want to do this intermediate step, this is actually a difference of two squares. X to the fourth is just x squared squared, and 1 is just 1 squared. So that means I should be able to use this pattern to help me factor. So that means this thing should be equal to 10 x squared minus 1 x squared plus 1. Difference of two squares. Uh-oh. You're not done yet. There's something else that can get factored in there now. What else can get factored in there now? Look at that, another difference of two squares. This is just like, this problem just keeps on giving and giving. Keeps on giving and giving. This is a difference of two squares. 10 x minus 1, x plus 1, x squared plus 1. All right, let's try this ugly looking one real quick and see what we get. First of all, is there anything in common? A 3. And what's the most m's you could pull off from all three? The minimum of the exponents. And what do we have left over? M to the 5th, or sorry, 10th. If I take out 2 of the m's and divide by 3, 54 over 3 is 18 m to the 7. Oh, and the next one's 17. Plus 17. Oh boy.
Yes.
I bet you could box and diamond this. Multiply to 17 m to the 10th power. Add up to 18 m to the 5th power. What numbers multiply to 17 but add up to 18? 1 and 17. And then, what should the variable be?
M to the 5th. Oh, shit.
5 and 2.
M to the 5th.
Well, I'm add. So if I want to add, I have to have the same. And it is m to the 5th times n to the 5th, m to the 10th.
Yes.
Times. So we're multiplying the top. When you multiply bases, we add the exponents. And when we add, we can only add like terms. So we know if there's only one term here, they have to be the same exponent. And can you add the same exponents together to get this one? Yeah, you do. You get 10. 5 plus 5 is 10. So if you box and diamond this young little laddie, you get, I don't even know what that means.
Wait a minute, I have a question.
I don't know what that means.
Wow.
But now you can play the factor by grouping game.
I
And
know
the
no one
fifth.
cares about this, but
Yes.
why is the left and right both end in fifth?
I'm embarrassed I said that. It is forever stored on that recording.
You said and then you
It says that 2x to the fifth is equal to 12x to the third minus 16x. Start by rewriting this so it's equal to 0. And we get 2x to the fifth minus 12x to the third plus 16x is equal to 0. And let's factor this completely. What's in common? A 2 and an x. What's left over? X to the fourth minus 6x squared plus 8. And this stuff is equal to 0. Claim you can box and diamond this, and you should get the following result. You use box and diamond, you get x squared minus 4 and x squared minus 2. If you use box and diamond, you can check on your own that this thing factors to x squared minus 4 and x squared minus 2 equals 0. So then what x's make each of this 0? You could even go farther and say that you could factor this thing a little bit more.
Why x equals root 2? X equals root 2 and x equals negative.
So then ask yourself, what x's could you possibly plug in to get you 0? Or you could solve a bunch of little one-step equations. This equals 0. What does x equal? Is one solution. This equals 0. What is the solution? What makes this group 0?
2.
What makes this group 0?
Negative 2.
And finally, what makes this group 0?
Positive root 2.
This one you may want to solve a little bit more on your own. X squared minus 2 equals 0. X squared equals 2. When we use the square root, you get x equals root 2. You're missing an answer though.
X equals negative root 2.
X is positive root 2. X is negative root 2. Give me a quick check. How many solutions do we have?
What? What happened?
There were 5 solutions. 0, 2, negative 2, positive root 2, negative root 2. What's the degree of this polynomial? There's something called the fundamental theorem of algebra that says that the number of solutions, real or complex, is always equal to 5. Whatever the degree is, not 5.